So our next test to determine if a series converges or diverges is called the ratio test. The ratio test is a pretty powerful test. It gets used quite often. So if you're asked to determine if something converges or diverges, the first thing you want to do is think, all right, is this a p-series? If it is, you're done. If it's not a p-series, then you kind of got to start thinking about other stuff. You think about the nth term test for divergence to see if it diverges. But if it doesn't necessarily diverge, then you maybe move on to the direct comparison test, but maybe you don't see a good function to compare it to. So if you don't see a good function to compare it to, you move on to this one, which we call the ratio test. The ratio test says that if you take the limit as n approaches infinity of the n plus first term divided by the nth term, and that limit is less than 1, the series converges. If that limit is greater than 1, the series diverges. And if that limit is 1, then, well, this test is inconclusive and you have to move on to something else. And we're going to prove why those first two things there are true. And then we're going to do a couple cases of this. And then we'll move on to what happens if it is equal to 1. So first thing to note is that this ratio test is once again dealing only with a series that has all positive terms. And that shouldn't be an issue because what can we do if our series does not have all positive terms? How can we make it have all positive terms if it doesn't? I'm not sure what you mean. If I have a series that does not have all positive terms, how can I make that series have all positive? There we go. That's what I was looking for. I can just take the absolute value of it, right? And so if I take the absolute value of a series that doesn't have all positive terms, then that new series now has all positive terms. And we proved yesterday that if a series converges absolutely, meaning if the absolute value of that series converges, we've proven that the series itself converges. And so that'll be good enough. So anytime we look at a series that doesn't have all positive terms, we're going to take the absolute value of it. And then at the end, we'll say, okay, it converges absolutely if it does. And then we'll say, and because it converges absolutely, that implies that it converges. So that's what we'll do. So let's take this first case here. Part 1 here, where we do this limit, we take the n plus first term divided by the nth term, look for the limit as n approaches infinity, and it equals some number that is less than 1. So the theory would be that if we get some value for this limit that is less than 1, we know that the ratio between the terms is less than 1 at some point for some capital N, which is just some value within my series, n equals 1, 2, 3, 4, 5, right? Somewhere for some n in there, I know that a sub n plus 1 over a sub n hits L. It gets very close to L. It effectively is L, right? And L is just a number, right? And so if L is just a number that's less than 1, some arbitrary number that's less than 1, I should be able to choose another number, and we'll call it R, right? Where R is more than that value of L, but still less than 1. Would you all agree that if L is just some number less than 1, I should be able to choose some other number between L and 1 and call it R? right? Since there's an infinite number of numbers between L, or between 0 and 1, let's say, and therefore an infinite number of numbers between L and 1 also. If L is just some number, I should be able to pick some number between L and 1 and call it R. And that means that because we've gone to some capital N value way out, maybe 100 terms in, and maybe 3 terms in, maybe 1 billion terms in, we know that for some value of n, the ratio between the n plus first and the nth terms is now less than r. Would you agree with that? If the ratio between the terms is L and L is less than R, then that ratio of those terms should be less than R as well. True? So if we take that capital nth term, where we end up with this ratio being L, we know that that term plus the next term, well, we'll say times the ratio, plus that ratio again times the next term, plus that ratio again times the next term, and so on, must be greater than our series starting at n. Would you agree with that? That if I take this term where the ratio between the terms is L, and I multiply it by R, where R is bigger than L, but still less than 1, and then I multiply by R each time, and R each time, and R each time, that should be greater than our series, the value of our series starting at n. Does that make sense or no? Everybody okay with that or no? You're all awfully silent, which makes me believe that nobody is okay with that. Oh, people are saying things. My chat wasn't like saying anything. Okay. Didn't tell me people were saying anything. Okay. Okay, can I please repeat that? Yeah, what part did you want me to repeat? All of it? So let's start back at the beginning a little bit. Okay, so I've got the ratio between my terms is L. That's what we found. We got some number, found that that L value is less than 1. So we've said, all right, L is just some number, some ratio between these terms that is less than 1. I can choose some value R that's between L and 1 because there are an infinite number of numbers between L and 1. And because we found this ratio, to be equal to L at some arbitrarily large value for n, doesn't matter how far away we go from n equals 0 or n equals 1, wherever we start, as long as at some point we hit this ratio of L, and that there's some value between L and 1 that we can call R, we could say that this term, this capital nth term, where we found our ratio to be L, that term plus the next term multiplied by R of some other, this is some other series, right? With the next, that same term multiplied by R a third time, and that same A sub n multiplied by R a fourth time, and so on, has to be greater than our series is if we started it at the value of capital N, because our series would look like, L times A sub n plus L squared times A sub n plus L cubed times A sub n. And since R is a larger value than L, these terms will be larger than these terms. Does that make sense to everybody? Everyone good? Delphine, did I get your question answered? You're good? Aiden, you're good. Yeah. Nick's good. Everybody that said they weren't good is good now. Okay. So this series right here, r times a sub capital N, r squared, a sub capital N, and so on. This just looks like what? It looks like a sub capital N times r plus r squared plus r cubed, and so on. And what is this series? This is just a, what type of series is this? It's a power series, and even better than just being a power series, it's a geometric series, right? This is a geometric series. And what do we know about a geometric series? What have we already proven about geometric series? That if the value for r is between -1 and 1, it should converge, right? And well, what did we get? We got that r is less than 1 and greater than this L value, right? And we're talking getting an L value here that's positive because we have all positive terms. And so this is a geometric series that will converge because the absolute value of r is less than 1. And if this series converges, and this series with the r's is greater than the series with the l's, then what does that tell us? It tells us that by direct comparison, our series, the sum from n equals 0 to infinity of our a sub s, also converges if it has this limit as n approaches infinity of a sub n plus 1 over a sub n less than 1 converges as well. Does that make sense or no? We're using direct comparison with a geometric series that has a term by term is greater than or equal to this series with the L's. And so therefore, if this geometric series converges, our series, which is always less than or equal to it, will also converge by direct comparison. Good or no? So Molly, we chose, well, we didn't choose r to be less than 1. I mean, we did, but we started with this first thing, L is less than 1. So we said L is less than 1. And then because L is less than 1, we can pick some other number R that is between L and 1. Because any number L that you choose that is less than 1 or greater than 0, doesn't matter what that L is, it could be 0.9999999 a million times. There's always some number R that is between that number and 1 that we can choose. So we choose an R value that is less than 1 so that we know that the geometric series will converge. And we then know that our series will also converge. Does that make sense, Molly? Yeah, it can't be less than 0 just based on the nature of these have to be positive terms. We're never going to have negative terms. So both of these values will be positive. So we'll never get a negative number out of it. Everyone good now? All right, what if L is greater than 1? This one's a lot easier. And if the ratio that we get between them is greater than 1, what does that tell us? If we start at, we'll just call it A sub capital M this time. A sub capital M is ending up, if the ratio is greater than 1, what's the relationship between A sub capital M and A sub capital M plus 1? Is A sub capital M greater than or less than A sub capital M plus 1? If the ratio is more than 1 between them. Which one is greater, the M or the M plus 1? Yeah, the M plus 1 is greater, right? So it should look like this. And what about the next term? Same thing, right? And so what's happening here? These terms are just getting larger, and we would be able to say that this just diverges by the nth term test. Because the nth term test says that as n goes towards infinity, we have to be approaching 0. And if these numbers are getting larger, we're certainly not approaching 0. Good or no? That's, I mean, the proof of part 2 is a little quicker and easier. So what we're going to do is we're going to see if we can find the radius of convergence of this series here. So nx to the n over 10 to the n. So how will we go about beginning this? Any thoughts? We're going to use our ratio test. But first, for all values of x, is this series positive?
Yes.
So for example, for x equals -3, when n is 1. 1 times -3 to the first is -3 over 10 to the first is a negative number. Right. This is not all positive terms for all x. So we'll say for all real x, not always positive, which means that we cannot immediately use the ratio test. Yeah, exactly. Yeah. Nick, you're good? Okay. Yeah. All right. So for all real x, this is not always positive. So what we're going to do then is we are going to instead, we're going to look at the sum from n equals 0 to infinity of the absolute value of nx to the n over 10 to the n, which is the same series, except now it has all positive terms. So we will use the ratio test. And so using our ratio test, what are we looking for? We're looking for the limit as n approaches infinity of the n plus first term of this series, which should be the absolute value of n plus 1 times the x to the n plus 1 over 10 to the n plus 1, all divided by the nth term, which is just the n x to the n over 10 to the n inside absolute value. Everybody good with that or no? So that's our setup. And what does that then look like? We'll have to flip the one in the denominator. So this becomes a limit as n approaches infinity of n plus 1 times x to the n plus 1 times 10 to the n all over, I'm going to put this inside my absolute values, all over 10 to the n plus 1 times n times x to the n. Everybody good with that? And what does that come out to be? First off, we could write this as n plus, well, we should write this as a limit as n approaches infinity of n plus 1. What about the x plus, or x to the n plus 1 over the x to the n? That should just be an x in the numerator. And then in the denominator, I should have just a 10 times the n. Everybody agree with that simplification? Just using exponent rules. And now this is just a rational function, essentially. Right? Our variable is n. X is just some number that we might plug into this. It's just some constant. 10 is just some constant. And so it's a rational function where the degree of n is 1 in the numerator and the degree of n is 1 in the denominator, which means all we have to do is divide the coefficients. Well, the coefficients are x and 10. So this should end up giving us the absolute value of x over 10. Good or no? Well, now what? Our ratio test said series converges if our limit is less than 1. The series diverges if our limit is greater than 1. The test is inconclusive if L is 1. We got absolute value of x over 10. Is that 1? Is that less than 1? Is that greater than 1? Okay, 1 second here. Shayla, you explain the evaluation. What evaluation part of, right, from here to here of the limit? Yeah, so the variable within here is n. X is just some number that we might plug into our series. X is just a constant. So this is just a rational function. It's xn plus x. Think of that as like 5x plus 5 or 7x plus 7 or something like that over 10n. So we have xn plus x over 10n as n goes towards infinity. Right? This is x infinity over 10 infinity, right? The infinities effectively cancel each other out. So it's just x over 10. It's just a rational function. But we have to remember that we're not treating x like a variable. X is not a variable within this summation. The variable is n. X is just some number that I can plug in. It's just some real number x. Does that make sense, Shayla? Okay. So our question then is the absolute value of x over 10 less than 1? Is it greater than 1 or is it equal to 1? And what's the answer to that question? Which of those things is it? The answer should now be, it depends. Right? Yeah, exactly, Nick. There you go. It depends on what x is. And so now we're going to treat x like it's a variable because now it is. Right? We want to know, when does this converge? What's the radius of convergence? So we want to know, when does the absolute value of x over 10 come out to be less than 1? And so that would tell us that the absolute value of x has to be less than 10. And so that would tell us that we know that this thing converges on -10 to 10 with a radius of convergence of 10. Good or no? Any questions there? Everybody okay with that? Yes, exactly, Nick. Our radius is just how much the x goes in either direction. All right, let's do another one. Let's see if we can find the radius of convergence for n factorial times x to the n. So once again, the first thing we want to ask ourselves is, does this have all positive terms for any x value? And the answer should be no, exactly, right? Because for some values of x, this is negative. So we're going to say this is not all positive. And so we will then look at this sum, n equals 0 to infinity, of the absolute value of n factorial x to the n. Good or no? Using our ratio test, we are now looking at the limit as n approaches infinity of the absolute value of n plus 1 factorial x to the n plus 1 over n factorial x to the n. Everybody agree with that? Okay. And what does that simplify to? X to the n plus 1 over x to the n is just an x, right? But what about n plus 1 factorial over n factorial? What should n plus 1 factorial over n factorial be? Not n. So n plus 1 factorial is n plus 1 times n minus 1, and so on. Whereas n factorial is n times n minus 1 times n minus 2, and so on. Right? So everything cancels out except for the n plus 1. So n plus 1 factorial over n factorial should just be n plus 1. Everybody good with that? All right, and so now the limit as n approaches infinity of this. Well, we have to think about when is this limit less than 1. If and only if, exactly, Adrian, if and only if x equals 0. Because if x is 0, I have 0 times n plus 1, which I can evaluate as 0 before I look at what happens as n approaches infinity. And I have then the limit as n approaches infinity of 0, which is 0. So this is the only case in which this limit is less than 1. We would say that the limit as n approaches infinity is of this n plus 1 times x is greater than 1 if we would say if x is an element of negative infinity to 0 union 0 to infinity. And so we would say then here, what is our radius of convergence? If it converges only at x equals 0. I think I briefly mentioned this yesterday. This tells us that the radius of convergence is 0. Right? And we would say that this converges solely for x equals 0. Good or no? All right. Let's look at this one. 3 to the n over 5 to the n plus 1. First off, for all values of n, because there's no x in this one, for all values of n, does this have all positive terms?
Yes.
Yeah, it does, right? We can say this has all positive terms, so we don't have to worry about throwing it inside an absolute value for this one. So we'll just go straight to our ratio test. Our ratio test should tell us that we want to find the limit as n approaches infinity of 3 to the n plus 1 over 5 to the n plus 1 divided by this, which would be the same as multiplying by the reciprocal of that, so 5 to the n plus 1 over 3 to the n. Good or no? And how can I simplify this down? 3 to the n plus 1 over 3 to the n should just be 3. But we still got 5 to the n plus 1 over 5 to the n plus 1, which I can't quite simplify down because of those plus 1s that are attached to it. But I should still be able to evaluate out this limit. How would we go about finding this limit? I could take out I could divide everything by the highest power, right? Isn't that something that we've done with limits in the past? Divide everything by the highest power. So I'm going to take the constant of 3 out. If I take 5 to the n, I'll divide that by 5 to the n plus 1 over 5 to the n plus 1. And then we'll have 5 to the n plus 1 over 5 to the n plus 1 over 5 to the n plus 1. And then what's 5 to the n over 5 to the n plus 1? Should be 5 to the negative 1. So that'd be a fifth. Plus, well, what about this one? As n goes towards infinity, this becomes just a 0, right? And then this one would become 1 plus another 0. And so what do we end up with as our limit here? We end up with 3/5. Everybody good with that?
Yes.
Yep. And what can you tell me about 3/5? It is less than 1, which tells us what? That this converges. Yeah, Delphine, going back to the last couple of those, we'd want to say that since we looked at the absolute value, if you didn't write that absolute convergence implies convergence, that's probably fine, because generally these questions are going to be more specific than what this one was, and you're going to have to do more with the endpoints and all, which we're going to probably not get to today, but at least get to tomorrow. And so they'll specify when they'll say when does it converge, when does it converge absolutely, when does it converge conditionally, which we haven't talked about yet, but that just means that it converges but does not converge absolutely. And you'll be putting a lot more specific answers at the end. So for now, if you don't write it, it's probably fine. Everybody good with this one though? No, there's no radius of convergence for this one, Nick, because first off, this one didn't have any x terms in it. So it's just a series. There are no, there's no worrying about, well, what about when x is 1? What about when x is 2? What about when x is 1,000? What about when x is -5? What about when x is 1/2? We don't have to worry about that. It's just this series. And so we came out to get a finite value for our limit. This series converges. There's no radius of convergence for it because there's no set of x values that we're looking at. All right, why don't you guys take a look at this one real quick and try to do your ratio test. All positive terms, right? Because no x's in here, and if n is positive, this denominator is positive, and it's 1 over that. So why don't you guys take a second and do your ratio test and see what happens. Ready to go? Yeah, Nick, I just saw your last question. No, the series does not converge to 3/5. The 3/5 is just part of the ratio test telling us that that series does converge. The ratio test with this, it all had all positive terms. You looked at the limit as n approached infinity. 1 over probably n plus 1 times n plus 2. And then that was being multiplied by n times n plus 1 over 1. Yeah. And we would note that if we were to distribute all this out, we'd end up with the limit as n approached infinity of n squared plus n over n squared plus 3n plus 2. And we know that's just a rational function. And if the degree of the numerator and denominator are the same, we divide, and exactly like you said, Adrian, you end up with 1, right? And so this is the first time we've come across this where our ratio test is inconclusive, right? This is in that part 3, where it wasn't less than 1, it wasn't greater than 1. We're not sure if this thing converges or not. So let's first off, maybe we can use the nth term test for divergence to prove that it diverges really quickly. So what's the limit as n approaches infinity of that term itself? What does that equal? should be 0, exactly. So this is our nth term test, right? So this is telling us, well, it might converge. So that's not very conclusive either. Let's try writing out some of the terms. Maybe that will help us. What's the first term at n equals 1? Should be 1 over 2. Right? And what's the next term? Should be 1 over 6. And the next term should probably be 1 over 12, and then 1 over 20, and so on. So, I mean, you know, those values, those fractions are getting smaller. Question is, are they getting small enough, fast enough for us to be able to say that this converges? Let's see, the series is decreasing, right? The values in the series are decreasing, and they're all positive. We could try to go in and use the integral test to determine if it converges. True? Isn't that another test we could use for a decreasing positive series? Could use the integral test, but the integral test only tells us if it converges or diverges, and this problem is specifically asking us to find the sum itself, find the sum of this series. And so I think what we need to do, how would we integrate this? Let's just think about that for a second. How would you integrate 1 over n times n plus 1? Nobody knows how to integrate 1 over n times n plus 1? That's a problem. How would you integrate 1 over n times n plus 1? Split it up and by parts. Neither of those are the exact answer I was looking for. Split it up. I'm hoping you mean split it up into partial fraction decomposition. Is that what you mean? Oh, good. Okay. Yeah. So we'll split it up using partial fraction decomposition. So let's do that. We're not going to actually do the integral, but let's take this and write it as a over n plus b over n plus 1, and say that that's equal to 1 over n times n plus 1, and solve this using partial fraction, and just rewrite it as a component of 2 different fractions. So that should be a n plus a plus b n equals 1. And, well, let's see, that would tell us that a plus b should be 0, and that a should be 1, therefore b should be negative 1. And so instead of trying to do the integral, because the integral will just tell us whether it converges or diverges, or potentially it will, let's rewrite this as the sum from n equals 1 to infinity becomes 1 over n, right, minus 1 over n plus 1. And anytime we see a series that sort of takes this form, 1 over n minus 1 over n plus 1, where it's two different terms in here being subtracted together within your summation, your best bet is to start writing out the terms of this series. Now, I know we already wrote out the terms of the series, but we're going to start writing them out this way. So what do we have here first? 1 over 1, right? Minus 1 over 2. Everybody agree with that? And then that gives us the 1/2 that we got. What's the next term? When I plug in n equals 2, this should be 1/2 minus 1/3, right? What about the next one? It'll be a third minus a fourth. And the next one will be a fourth minus a fifth. And then a fifth minus a sixth, and a sixth minus a seventh, and so on, right? Well, what do we notice happens to the majority of these terms? They should cancel out, exactly. So the negative 1/2 should cancel out the positive 1/2, and the negative 1/3 should cancel with the positive 1/3. And this negative 1/4 will cancel with a positive 1/4, right? That'll be in the next term, and that'll have a negative 1/5, which will cancel with the positive 1/5 in the next one. So effectively, all we're really left with is that very first term. And well, if we ever were to make it to infinity, we'd be left with that infinite term also, which would be equal to the limit as n approaches infinity of 1 over n plus 1, right? This last little, the second piece of each of these terms. And what's the limit as n approaches infinity of 1 over n plus 1? Should be 0, good. Which gives us a sum for this series of 1. So if I sum together 1 over n times n plus 1 infinitely, I get 1. And if we'd done the integral test, we would have seen that it converges, but we wouldn't have necessarily known the exact value that it did converge to. This type of series where we had to break it down using partial fraction decomposition, and it's not always done using partial fraction decomposition, but where you break it down into like a grouping of multiple terms being added or subtracted within this summation, I mean, usually with subtraction, we call these a telescoping series. And the reason they're called telescoping series, you think about like, you know, old school telescope, right, that like collapses in on itself, right? So like that's basically what this is doing. You can extend it out and write it as 1 minus a half plus a half minus a third plus a third minus a fourth, but you can also just shove it all together and cancel out all of these terms to just get that first and the last term, just like the telescope will collapse in on itself. And they call those telescoping series. What was your question, Nick? How did I get to the limit step at the end? Yeah, so everything cancels out. This minus a half and the plus a half and the minus a third and the plus a third and the minus a fourth and the plus a fourth. They all cancel, right? And going on forever. The 1 doesn't cancel out. And the limit as n approaches infinity of n plus 1, or sorry, of 1 over n plus 1 is the second half of this. It's the minus 1 over n plus 1. That when I finally, even though we don't actually get there, when we finally get to the infinite number of terms, this last piece of the last term doesn't cancel out. And so we look at what's the value of that as we go towards infinity. And since it happens to be 0, it just becomes 1 minus 0. This last little limit thing will not necessarily always be 0, though. So just be a little bit wary of that if you see something like this. Telescoping series. Everybody good or no?